Hey there, YouTubeistas. My name is Kirby Erner, and here I am at my Facebook page, and behind my head, now that's not really me, right? That's an icon I took from Subgenius, which is kind of a spoofy cult. Anyway, I have more about that in other videos. Behind my head, though, or Bob Dobbs's head, is a gigantic tensegrity sculpture. It's a picture I took in Baltimore when I had the good fortune to share a few days with the Hubble Space Telescope instrumentation and other staff, ground faculty, right? People actually process the signal from Hubble and schedule Hubble, keep it, moving, rotating, doing experiments. And that was a 3 day class, more or less, as I recall, in the Python computer language. And what I do is I do what I call a futuristic high school. Like, I want to be a few years ahead, maybe, in terms of topics covered, but also how we cover them, what the technology is, what the toys are, what the artifacts are. So I have collaborators. I have people who market materials like teaching materials, which you see often on this channel if they fit into the curriculum that I'm working on. For example, this is a rhombic dodecahedron. It's a space filler, and it's also what would surround every ball in a ball packing that's studied a lot in science, crystallography in particular. And so it also has applications just to basic geometric thinking. You want to do CAD, computer aided design. You want to do Blender, a Python project or product, and you want to do animations, cartoons. So we're in the world of what's called design science, which does have heft to it. It's not all about stuff on the screen. You can have heavy. Design science includes, like this very toy here is pretty heavy because it has magnets in it and stuff. In fact, how big a structure you can build with these various toys is interesting. There's limitations based on weight, based on compression and tension properties. So if you've seen some of my other videos, and even if you haven't, this will make plenty of sense. You know how high school kind of is now, perhaps. There's a lot of emphasis in the math part on polynomials, and in Python we have something called SymPy. We can get output using really mathy looking notations. We can do LaTeX, it's called. Now, if you have experience with Mathematica, you know that you can do all this stuff in Mathematica also. The thing is, the budget here, we can do it with an integrated approach. In other words, the same language we're using to study math, Python, we can also use to build very simple websites. We can talk to databases. And when it comes to polyhedrons, they have a database aspect. In other words, where do we store all the coordinates? Where do I save my rhombic dodecahedron or my icosahedron when I've finished working with it? Do I put it on a shelf? Literally, I might do that if it's a literal polyhedron, but if it's going to be a screen-based polyhedron, then I need to store it in a database, perhaps. And there's a long tradition going back. I'm not claiming priority, originality, or first on the block to be doing any of this at the moment. Like Fermat's primality test, that's a long, big topic, and I've been flashing through that we have YouTubes about it already. One of my goals with these kids, I'm starting a class tonight, in fact, this evening, is to familiarize them or help them familiarize me, it's a two-way street, with who are the YouTube channels, personalities already out there, like Mathologer and Numberphile. Of course, the red and is it red and black pen or black and red pen, and then there's three blue ones. I don't know why all these color references, but it makes some sense, right? Three blue, one brown, is it? Socratica. So I don't know if that's a normal thing for like a traditional high school teacher to do, to try to be advertising YouTubes. But like I say, this is more or less a futuristic high school. And I bill it as such. It's like, here's a skill. Let's just end this with a skill. If you're familiar with GitHub, you can go to, say, my School of Tomorrow repo. I'll put a link. And then you can scroll down, and any of these that end in IPYNB, those can actually be rendered in something called NB Viewer. You can try to open it first in GitHub, and it may well work. It may also not, because they have it's kind of a kludge maybe how they do it. But anyway, see, something went wrong, right? Don't worry about it. Go to nbviewer.jupiter, spelled with a y.org, and cut and paste the very same URL. There's the whole GitHub address into the blank that you get on that page, and hit go, and it will render the same thing. And it will render it a little bit better, actually, than GitHub would if GitHub did, which it often does. And I've got these animated GIFs in here, and what we look at as we scroll down is the kind of advanced high school topics with Python that we learn in our School of Tomorrow, you could call it, right? It's like we're a little bit ahead of the curve. We're doing stuff with cryptography. We're doing stuff with Fermat's Little Theorem, Carmichael numbers. And I just found out, this blew my mind actually, that the coefficients of Pascal's, you know, the binomial theorem, right? And every row of Pascal's triangle is a successive expansion of x plus 1 to a power, or x minus 1 to a power. If you don't really care about the sign, it doesn't really matter in terms of what the coefficients are. And it turns out that if the row you're on, like the 12th row, divides evenly into all the coefficients, then 12 is prime, which it isn't, and so it doesn't. But something like 10, or here I'm using the, I'm just proving this not proving, I'm verifying that this works up to a point, and that I'm expanding a polynomial using SymPy. I'm expanding x plus 1 to the p, because it doesn't really matter if it's minus 1 or plus 1. You get the same coefficients. And then you throw away two of them, the first one and the last one. You don't want in Pascal's triangle, you're getting rid of the ones. And then you don't need all of those coefficients because it's symmetrical, right? They go up to a middle, and then they may repeat. If it's an odd number, it will, and then goes down again the other side. In other words, you're going to get a lot of symmetry with these coefficients. Let's see if I have them printed out here somewhere for one of the Pascal triangles. I was doing that recently. Cryptography, prime numbers. What I just found out, as I was saying, is if you can divide, like, say, okay, here we go. Here's the coefficients for the 19th row, we'll say. They are, right? I computed it. There's the binomial theorem. You can just import binom from the math library if you want. All right, so get rid of the ones, the first one and the last one. Keep the 19, and just ask, is 19 divisible? Does it divide into all of these? And you only have to go up halfway, because then they repeat. Keep the 19. I do a reduced GCD, like get the greatest common divisor of all these numbers. And if it is 19, if it is the first number, whatever that number is, then that number is prime. So that's what I'm playing around with here. It's called the AKS test. And it's supposed to be if and only if, right? So that's news to me. Learned it yesterday, testing it out, having a good time with it. That's what I call learning. So same kind of process I want my students to pick up on. You know, just verify, check. If you know the meaning of something, whether you know the proof or not, you should be able to verify it, get it to do its tricks, show the significance of the theorem, even if you don't know how to prove it. Like I don't know how to prove that one. Okay, thanks for listening. See you next time.